What up, what up, what up? Let's come at you live with section 4.3. This is on maxima and minima. These are called the extrema. Extrema is it describes max or min. That way, if you don't know what it is, you just call it an extremum. Maxima is the plural form of maximum. Minima is the plural form of minimum. And extrema is plural form of extremum, which sounds weird. But an extremum is a max or a min. So let's look at it graphically. I think this is the easiest way to interpret it, get an understanding of what's going on. Let's say I have this crazy function here that's in the like peach color. Everywhere that there is a mountaintop or a cusp would work too. We have a maxima. Now, if it's the so notice like everywhere I have a hill right here. Let's see let's do the highlighter. Highlighter worked great. You got a point there, that point there, that point there, that point there. Those are all maxes for in an area around them. They're the tallest point in the region. And if we look at the lowest points, we got a low point there, we got a low point here, we got a low point here, here, and it looks like it's getting like it's hard to tell what's going on right there, right? We're gonna discuss that later. Like having a wiggle like that. And it's kind of hard to see what's going on. So those are all called local maxima or local minima. Where the tallest point is called the absolute max. And where the lowest point is called the absolute minimum. Okay? Absolute does not mean the absolute value of. It just means it is the biggest or smallest, lowest. So the absolute, we have an absolute max at C1 right there. It's got the value, the absolute max at C1 is actually, we'll talk about that in a second. The absolute max, no, we'll talk about it now. The absolute max is this value, whatever that value is. So we say that's the absolute max, f of C1. The absolute min is at the lowest point. We plug in C2. We find out what this value is. That's the absolute minimum. We'll talk more about that later in a second. We've got a lot of like descriptions and definitions and theorems going on before we get to some practice problems, but it helps to see all this stuff graphically. Okay? And this is over an interval. Now, we could do a closed interval where we cut things off, as we'll see later on, where we have endpoints. If we've got endpoints, we've got more stuff to consider, but let's wait till we get there, okay? We got some more examples right here. The top three have infinite domains. They keep going on and on, negative infinity to infinity. X cubed doesn't actually have any max or min because it keeps going up or keeps going down. Okay. These keep going onward, but it looks like they're going to 0, but it doesn't look like they actually cross 0, and they can't because the function there has a 1 on top, and fractions only equal 0 when the top equals 0. Okay. Cosine, this thing is a wave. Remember, we got a wave going on, and it keeps going. So everywhere we have a peak, which happens to be at 0, 2 pi, negative 2 pi, we would have 4 pi over here, negative 4 pi over there. Those are all absolute maxes of 1 at those points. And then the absolute min are at the multiples of these. Plus or minus pi, plus or minus 3 pi, plus or minus 5 pi. Have points over there. That's an absolute minimum of negative 1. And if you're ever confused about how we phrase it, I mean, I have phrased it the same way. Notice the wording here. Absolute minimum of, or maximum of 1 at x equals 0 on this graph. Okay? So we don't say this point here is 0, comma 1, but we don't say that's the absolute max. We say that's the max. And then we say where it's at. Okay? Notice that's an infinite domain. It doesn't show it, but it keeps going on and on and on. Now we look at some ones that have like a closed domain. So I'm going to do this, move that point. Oh, shit. Don't move it. Never mind. I can't move it. So on this one, we've got this weird function right here. Look at that. And when you graph it, we can see the tallest point is right there. So we have an absolute maximum of 2, and that's happening at 0. And then the lowest point looks like it's right here, but we don't really have a lowest point. As we saw in the getting ready for this section, the closer we get to -2, I can actually get a value that gets closer and closer and closer. If I thought that -1.99, is that the lowest? No, I could do -1.999. Is that lowest? No, I can keep adding a decimal place and getting lower. So when we have this open point right here, it means we don't have a max, or we can't actually get to that point, which means we don't have a max or min if the hole was up top or something like that. Okay? So there's that. And for those that are lazy and don't watch the video, I will make a point of saying, no, it keeps going. Add more 9s. Because I know some of you are not watching this, and it's very disappointing. All right, next graph, we've got x minus 2, that quantity squared. We're going to do it on 1 to 4. When you graph it, we can see we've got value. We got our smallest value is right here at x equals 2. The value is 0, so that's our absolute minimum. We've got a maximum up here where the x is 4, and it happens to have a y value of 4 there also, okay? So we can see all this stuff graphically. Here, we have a min here at 0, where the minimum is 0, but notice this is following an asymptote. So the closer I get to x equals 2, and I'm going to say 2 from the minus side, the larger y gets. And it's doing the same thing, the same issue we had over here. Same issue we had there. So that's examples of kind of like what's going on. We have something called the extreme value theorem. It is proven in upper division math courses. There's a course called Real Analysis. As an applied math major, it was optional for me. I did take it. I didn't have to. If you're going to be a pure math major, you'll have to take it. The extreme values theorem says if f is a continuous function, it has to be continuous, and it's gone a closed and bounded interval a to b, then there is a point in AB where F has an absolute max and F has an absolute minimum. And we'll take a look at more of that more in a second. But the idea is, and we abbreviate this EBT. For the EBT to apply, that it has to be continuous. It has to have a closed and bounded interval. No A comma B, no bracket A comma B with the parentheses, or parentheses A bracket B. None of that. None of those apply. It has to be brackets on both sides. That's what makes it closed. If the interval is, so if it's open in any way at any of the points, or if there's a discontinuity, the extreme value of the theorem doesn't apply. That doesn't mean there isn't an absolute max or an absolute min or absolute extrema. It just means there's not guaranteed to be one. Okay? So that's what we had circled up here in yellow, the absolute max and min. Then we have local maxes and local mins in blue, and we're going to talk about those next. So those are called the local extrema and critical points. A function has a local max at C if there is an open interval I that has C in it. This is okay. The math jargon here is rough. Let's look at this pictorially. I got a picture here that we're going to look at. So like we're going to do some small, let's do white here. Nope, let's do pink. Purple, let's do purple. So I'm going to zoom in right here. And we do a small interval around it. And let's say this value is C1. F of C1 is greater than f of x in that small interval. Same thing down here. Not what I wanted to do. Ooh, almost erased my graph. And again, I wanted to cut off the line there, so let me do that. We'll have like a little line cut off here where our interval is like that. We'll call this point C2. F of C2 is less than or equal to f of x everywhere in that small interval. Okay? It is important to note that cusps work as well. And I didn't put the dots on the point yet because I wanted you to see it's a sharp point. But that's a local max. And that's a local min. Okay? So we have local maxes there. I've got my absolute extrema listed. The one on top. This one, this value is just a little higher than this value, so that's the absolute max. And this value is a little lower than this value or this value, so it's the absolute min. Now, it's important to note that we don't call this point or this point a local min. They are not local mins because I can't do some small interval around it. If I do a small interval around it, my graph doesn't exist over here. So not a local min. Okay? We got to have it on both sides. So the absolute values can occur there. Not absolute values, the absolute maxes and absolute mins can occur at endpoints, but the local maxes and mins cannot. Now, pictorially on this graph in blue, it was easy to see the maxes and mins. You just look for the high points and the low points. Some graphs it isn't. So this function here is y equals e to the negative x sine of 10x. That's what exp means, e. And you can see that they show what the values are, show where it's at. I've got a point there, a point there. Notice the little gray dots there? We can see them. These are all local maxes or local mins. All right, let me hit my ringer off. There we go. But notice as we get closer and closer, like I can tell the difference between a max and a min, but at some point I can't. What's going on here? Oh, wow. Okay, that doesn't scribble. Let's just do that. We don't know what's going on here. Which are max? Or just zero? Because this graph shows zeros right here. We got our zeros. Those are all zeros, the green ones. But it's kind of hard to tell, like, which one's which when we get over here. Okay? So we have a way of addressing that. Ooh, don't want to fuck with that. So we're going to say a critical number, critical point. We don't say critical number. Well, I guess it is a critical number. Critical number is where f prime of c equals 0 or f prime of c is undefined. Okay, and that says that we got that there and there. The highlighter doesn't work well on this stuff, unfortunately, so I won't do it. But we call the actual point where we have a coordinate system, the critical point is the whole xy, which is c comma f of c. Okay? So we can find local extrema by setting the first derivative equal to 0 and solving for it. And finding where f prime of x is undefined. And some guy named Fermat came up with this. I'm sure that was his last name. If f has a local extremum at c and f is differentiable at c, then f prime of c equals 0. His theorem only covers this part. It does not cover that part. But we do have this information right here that says the undefined part. Okay? And we can see, we saw those up above. On the cusps, when you take the derivative, are undefined, kind of like absolute value of x. Show up very well. Absolute value of x doesn't have a derivative at 0. But it has a minimum there. So it is important. If you want to see a proof, if you're going to be a math major, You should look at the proof. It takes advantage of the intermediate value theorem and the limit definition of the derivative, and they do like approaching it from the left is less than 0, approaching it from the right is larger than 0, or vice versa. And they end up showing that it actually has a 0 there. It is important to note it is a one-way theorem. All local extrema meet Fermat's theorem, but not everywhere f prime of c equals 0 is a local extrema. All maxes and mins have a derivative of 0. Okay? But it's not enough, okay? So here's an example looking at it. Like here's the absolute value I was telling you about. Absolute value here, if we put c right there, the derivative is 0, but it does have a local minimum there. So the local minimum exists, but we don't have, it's not 0 and it's not, okay? We have a local max here at the cusp, but the derivative is not 0. So just because the derivative is 0, so the local max or local value or the local max or min will be where these are, but here's an example of where it's not true. The derivative here is 0, but that is not a max or a min. The derivative here is undefined, but that is not a max or a min. I'll change colors for that. Right. Yeah, I think you saw it. I don't want to interrupt it. So these two have a derivative where it equals 0 or is undefined, but are not local maxes or mins. Okay? So to give you one that you know a little bit better, like f of x equals x cubed. If we take the derivative, we have f prime of x equals 3x squared. At x equals 0, the derivative equals 0, but it is not a max or min there, okay? So the critical points are only candidates to be a local extrema. All right? All right, I'll pause this video. Next video we'll do locating critical points.